Hello everyone, welcome back. In the first video we defined success probability as half, and you had a plus half trace of pi 0 times the operator d, right? And there d was defined as the following: alpha 0 minus alpha 1 alpha 1. All right, but analyzing the properties of d, we showed that d can also be written as delta pp minus mm, and delta is a real number, and where delta is nothing but plus minus sine theta, where theta is the angle between alpha 0 and alpha 1. All right, so let's plug this expression there back in PS, the success probability. Then PS is nothing but half plus half trace of pi 0. Okay, I forgot pi 0. Trace of pi 0, and then you have delta pp minus delta m. Okay, so now you can do some mathematical manipulations again. So I can take this delta out, as trace is a linear operator, and I can write this as delta by 2, and I can go the other way around from trace back to the inner product, and then what we can write is p, and you have this pi 0 p, right? Because we are using the same identity when we went back from where we started. All right, I mean we are using the same probability identity, trace of just a second, trace of BA is equal to AB. Okay, we're using that. So then the next term would be m pi 0 m. Okay, now I want this to be maximum. Okay, and I want this to be maximum, then this half is here, this is a positive value, so this one I want this to be 1, which can at most be 1, and I want this term to go to 0. All right, because you have a minus sign before. So if this term goes to 0, the second term, and the first term is, if this term is here and gives you 1, then your success probability is maximized. All right, that is what we have been trying to do since the very beginning. We said that pi 0 and pi 1 were our choices, right? Or if I just choose pi 0, then pi 1 is fixed. So I can choose pi 0 in such a way that p just gives me p. Okay, then this first term here would just give me 1. Okay, and I can obviously choose pi 1 on m is equal to m. That would imply, you can check it by yourself, that pi 0 on m is equal to 0. And then this would imply that this term goes to 0. All right, so what does it mean? It means that, if you remember correctly, that okay, I had this alpha 0 and alpha 1 here, and I had this choice of choosing pi 0 and the perpendicular direction pi 1. Okay, and I want to choose pi 0 in the direction of the eigenvector of the operator d, which is p. Okay, then automatically this vector will be in the pi 1 direction, m. And I can obviously choose that because pi 0 and pi 1 are orthogonal to each other, and p and m are orthogonal to each other as well. So I can obviously choose pi 0 to be in the p direction, which is the eigenvector of the operator d. Okay, so that will maximize my success probability. So the conclusion after all this calculation is that an optimal measurement to discriminate two non-orthogonal states alpha 0 and alpha 1 will be with a measurement relative to the eigenbasis of the Hermitian operator D. Operator D, which is defined by the following equation: alpha 0 minus alpha 1 alpha 1. All right, and your the optimal success probability will be half plus delta by 2. Okay, let me not write sine theta now. So if you check that I want the first term to go to 1 and the second term go to 0, then that would not be nothing but 1 plus half plus delta by 2. Optimum, okay, let me write it properly. So PS optimum will be nothing but half plus delta by 2, and this is nothing but half 1 plus sine theta. Right, now you can see if theta is equal to pi by 2, that means alpha 0 and alpha 1 are orthogonal. Okay, then if you ask yourself intuitively, if alpha 0 and alpha 1 were orthogonal, then we could distinguish them by a measurement, right? That was the very first thing that we said in the very beginning of these videos. And if this is pi by 2, then PS optimal is nothing but 1, right? So whenever theta is pi by 2, that means the angle between alpha 0 and alpha 1 is 90 degrees. Then you can obviously choose a basis such that you can obviously perform a measurement and you can distinguish them perfectly. All right, and that's the idea, and this is the optimum success probability for non-orthogonal states. All right, so this has a name, and this name this is very important. This name is called Hellstrom. Sorry for the spelling, just a second. This is called Hellstrom Holevo bound. That means your success probability cannot be more than this. All right, so let me just state the theorem, the Hellstrom-Holevo bound for pure states. So let me write it down for you. So given one of two equally likely states alpha 0 and alpha 1 with alpha 0 alpha 1 modulus is nothing but cos theta. The probability PS of correctly identifying the state by any quantum measurement process is bounded by PS is less than or equal to half 1 plus sine theta. Okay, and the bound is tight. That means that there is a particular choice of basis that, or particular choice of measurement that gives you the equality. That is the eigenbasis of the operator D. Alright, and this is called the Hillstrom-Holefer bound. Right, I hope that it is clear to you. This was a bit mathematically challenging, but if you have any confusions, please let us know and we will try to clear it for you. Alright, thank you so much.